Good afternoon. I'm Anil Elandur. Thanks for the introduction. So I'll be talking about e-commerce anomaly detection, applying tensor decomposition using a natural gradient-based inference. It's a work with Bamdev Mishra as well. So I will introduce the problem setting, describe the model a little bit, and then the inference techniques. We'll look at some experimental results and finally conclude with summary and possible future work. So what are the e-commerce anomalies? In fact, there are many, but in this talk, I'll be focusing on the anomalies caused due to the seller incentivization of reviewers. Right. The way this happens is sellers, pay reviewers to write fake reviews about, like good reviews about their own products, and then fake bad reviews about their competitors because he wants to like increase the rating, his own rating, and decrease the rating of his competitors. This is not ideal because in e-commerce people depend on reviews before they make a purchase decision, and hence we want to catch these bad actors. And if you see this is a real Facebook snippet where a seller or an agency is soliciting reviewers, saying he'll pay them some money to write a review, and he's even saying that it'll take just 1 or 2 minutes to write one. So what are the key signals? So the most important signal is that the entities soliciting fake reviews form dense bipartite cores with their fake customers. The reason is the following, right? Typically at any given time, the entities over here shown on the left, or the sellers, go through some common intermediary channel for recruiting these people who are waiting to be paid for writing a review. So when we look at, so these are clearly temporarily clustered, right? So what happens is at a given time, all of these people are looking at almost similar set of customers, and hence there is a dense bipartite connection between them. And of course, fake reviews have similar ratings because some people might have paid them to write 1 and 2 stars, and some people might have paid them to write 4 and 5 star ratings for their own products. So given this, our goal is now to detect these dense bipartite graphs satisfying the lockstep behavior. Right? The input data is a tensor because it incorporates the review timestamp, the players, the seller and the reviewer, the rating as well, the product, which product was given that rating. So we have applied tensor decomposition to detect the dense scores between the sellers and reviewers. And we have enhanced that to do semi-supervised learning because we have some label data which are input as binary targets. We have label data for a subset of the entities. Could be sellers and or reviewers. And finally, we have developed partial natural gradient learning for inference of all the latent variables in the model. So this is the model that is from Piyush Rai et al. That appeared in ICML 2014 paper. Basically, so we are dealing with binary tensors here because the element of each tensor is an association. So a reviewer wrote a review or gave a rating for this product from this seller at that time. So that is an association. So it's a binary tensor. So each element of the tensor is assumed to be sampled from a Bernoulli logistic function. This equation here is a CP decomposition equation. Basically, you have tensors of rank 1. You take the outer product. It's almost very similar to SVD. Lambda is a diagonal tensor, or you can think of it as a scalar. and R is the rank, the low rank approximation of the tensor. So we have lambda and u as the latent parameters that needs to be estimated. Lambda has a normal prior with the variance tau that is determined from an multiplicative inverse gamma process. It's a non-parametric way of determining the maximal rank of the tensor. And then U also has a normal prior with variance mu, and we have given inverse gamma hyperprior because when we do semi-supervised learning, we wanted to control the sparsity of the factors. So we have taken this model and we have enhanced it to do semi-supervised learning. Right? We have some known abusive entities, and these are treated as binary targets. And they have a label +1. And then we will do tensor decomposition by simultaneously incorporating this label data. Because the intuition is that the patterns hidden in the known abusive entities can be leveraged to discover more entities with similar signatures. And this is some notation there. So the way we link the labels is we treat the factors as the covariates and then have a logistic transfer for determining the label. So basically we want to determine these coefficients as well. Right. To get closed form updates, we introduce auxiliary variables that are Polya gamma distributed, determined or denoted by nu. And actually this slide will clarify that. So we have a logistic link between the covariates U and the label Z. So what needs to be determined are the betas. And if you take the gradient, as most of you would know that you don't get updates in closed form. So with the introduction of nu, which is Polya gamma distributed, the joint likelihood now looks like this. If I take the log, then you notice that it is a quadratic function of psi, which is inner product of the beta and u. So it's a quadratic function in beta that you're trying to determine. So clearly you will get closed form updates. The paper by Piyush Rai for the unsupervised tensor decomposition has used or compared Gibbs sampling versus online EM with sufficient statistics. And they have shown that online EM is a much better inference technique than Gibbs sampling, both in this terms of speed as well as the performance. We have actually online EM with sufficient stats is a scalar update of the parameters. So we do vectorized updates using stochastic gradient ascent. And we have also focused on, actually in this presentation, I'll focus on natural gradient ascent. So what is natural gradient? It is, you take the Euclidean gradient and you multiply it with the inverse of the Fisher information matrix. And there are a few intuitions of why it is good. The first one is that natural gradient uses a quadratic approximation, a local approximation of the cost function. And the second is it makes the contours of the loss function more spherical. So you take almost equal steps in each iteration along all the directions. So you converge faster towards the optimal. But there are challenges, right? So because you need to compute the inverse of a matrix. And in our case, that matrix could be of very large size, typically in the millions. To circumvent this, we exploit the problem structure. As you saw that with the introduction of Polya gamma, the latent parameters are basically, the loss function is basically quadratic in nature. In fact, it's quadratic in lambda and u because in Piyush Rai's paper, they also introduce Polya gamma variables. And because these are quadratic, we can work with the diagonal blocks of the Fisher information matrix, right? Because it is, the diagonal blocks also have a positive definite structure. Hence, there is convergence guarantees. And each of these diagonal blocks are very small in size. They are of the size that we have of size r by r. R is the rank, that the low rank approximation of the tensor. In fact, this pictorially shows that this is the Hessian structure, right? We work, if you want to update lambda, we only use you take this block and compute the inverse, and so on. And we have implemented stochastic partial natural gradient ascent using small mini batches for scalability. Again, most of you might be familiar with this. It's basically how you compute the Fisher information matrix. There are two expectations. The outer expectation is with respect to the data, which is replaced with q hat of x. The inner expectation is with respect to the likelihood model that is assumed. In this case, it's a logistic model. And the expectation is with respect to the gradient of the covariance matrix or covariance of the log likelihood. Gradient is with respect to the parameters theta. Or it can also be written like this. You take the Hessian and you compute the expectation with respect to the likelihood model. This is also using another property of the Fisher information matrix, where if you have IID or conditionally independent samples, the Fisher information of your data is basically the sum of those, sum of the Fisher information of each. And this paper actually talks about it in much greater detail. So in our case, so this is the, for example, for lambda, this is the cost function. This term is the joint likelihood, where omega is the Polya gamma distributed variable. Yeah, sure.
In the previous slide, you replaced the covariant structure with the Hessian. Is it particularly true for your problem?
It is.
Okay, right. It's not generally
anything that has, if you take the gradient of the integral, it should be 0. Gradient of the integral of the likelihood function should be 0. And in this case it is. And I checked out that I did computed both cases and it was true. I verified that, it's verified. In general, it is not true. It's only under that circumstance that the gradient of the integral should be 0. Because the integral gives you the constant. It sums to a unity or something, and then it's, yeah. So, yeah, so this is the cost function with respect to lambda. And this is the omega or Polya gamma distributed. Sorry, yeah. So this is the joint likelihood. This is the prior. Right. One thing to notice is this is a joint likelihood. Actually taking the Fisher information, calculating the Fisher information with respect to omega as well is very complex. So we basically integrate out, so we basically integrate out omega using this identity here. The other thing to notice is that this is not normalized. So to normalize this, it's not in a closed form. So this is a normalized likelihood. Eliminating omega, miraculously it ends up in a nice closed form here, and this is normalized. In fact, normalizing this, because this is likelihood with respect to y, is very simple because y is discrete. It's a binary. And this is how the likelihood ends up with. So we compute the Fisher information for this likelihood. And it's applying the straight Hessian formula. You take the expectation with respect to y of the Hessian. And the sum is because you have many such samples from that mini batch. And you end up with this matrix. Where A is not defined here. It's defined in the archive paper that we have put. It's basically not a function of lambda. It's a function of u. And n is computed in this way. In fact, if I use just the Hessian without taking this expectation, it's of the same form except that n is in the form of a tan hyperbolic phi by 2. So they are very closely related. The tan hyperbolic has a longer tail and drops off slowly. This drops off fast. And if you take the inverse, basically you're providing a higher scale or taking longer steps in the optimization. That's why both are very comparable. This is slightly faster. The natural gradient is slightly faster than the Hessian in this case, because both have almost the same form. The prior term is accounted by considering its precision as a conditional, kind of guaranteeing positive definiteness. So we look at some results. In fact, this is old. What I'm showing here is relative numbers. The maximum value gets 100. Basically, the takeaway here is that the AUC improves with semi-supervised versus unsupervised techniques. The natural gradient has the best performance. The sufficient statistics actually takes a long time to converge because it is doing scalar updates, as I mentioned before. The problem with stochastic gradient is that it overfits. Because we have u, the factors, and beta, both are undetermined, and we are doing it in alternate fashion. This natural gradient shrinks a lot of the dimensions of the factor of the u of the factor matrices faster, much faster than stochastic gradient. That's why this tends to overfit, as we see in this graph here. The blue line is the stochastic gradient. Again, the AUC values here are scaled. This is the train AUC, this is the test. This is using the target we are trying to predict are which sellers might be abusive. The thing to notice is that the stochastic gradient has the highest train AUC. It's overfitting on the train set. And the test performance is little subpar. The natural gradient almost has the similar performance on both train and test. The sufficient stats is very slow in converging, as this is still not flattened out, and or here it's very slowly increasing even after 6 epochs. And of course, all of them were given the same routine in terms of the learning parameter, same batch size. Everything was the same except that one using partial natural gradient, one using sufficient stats, and so on. So to conclude, I would say that we have applied a tensor decomposition to detect one kind of anomaly, right? Basically, we want to detect bad actors, maybe sellers or reviewers, because once you get the bipartite graph, you get both of them. And we have shown that we could apply partial natural gradient learning to this problem by exploiting the quadratic nature of the loss functions. and empirically shown the efficiency of using partial natural gradient learning. One thing we could also try is try deep learning for tensor decomposition, given the equivalence between tensor decomposition and convolutional rectifier networks. Yeah, that's where I would end my talk. Any questions?
Any questions?
Hi. So I had when I was looking at the Hessian decomposition that you showed, the block structure, I was reminded of all these limited memory Newton techniques that one has, like LBFGS and all, and they're basically trying to solve the same problem. It's difficult to invert the matrix, and you still want fast to invert matrices. Would it be worthwhile trying some of those? Because in terms of, I think if the blocks here are R by R, one would equivalently want to get a rank R approximation to this matrix, which can be updated in online fashion and all. The benefit that might come is because right now here the covariance structure between lambda and the various UIs is lost because they are all zeroed out.
Right, correct.
Those would preserve those correlations or whatever a bit more.
Actually, yes. I mean, so the loss function is quadratic, right? So you still have convergence guarantees in this, but it'll be slower than considering the covariance between the lambda and U, the preservation. Yes, I mean, that's the only, we haven't tested out how slow it is going to be with this approximation of the diagonal blocks.
So is that because we wish to do the updates for lambda separately, U1 separately, and UI separately?
That's what we end up doing. So, and one benefit of doing that is now you could parallelize it because you're holding everything constant.
But if parallelization we can, I mean, if it's matrix vector product, that can be parallelized even if we had a low rank matrix instead of a block diagonal structure. So it depends on how we parallelize the matrix vector operations. Yeah, of course, this is very convenient. This is
we haven't tried that, but okay. We can discuss that often. So you're saying you approximate this matrix?
Yes, a different approximation. Instead of blocks, basically this is a sparse approximation to the matrix. That would be a low rank approximation, and something in between or some hybrid thing might also.
Point. Yeah. I haven't tried that, but we'll certainly.
So similar to what he was asking is, it would be more efficient to maintain the inverses as you go along, like LBFGS or something, as opposed to this and doing inversion as you go. The second part is, did you say that you're doing it in a mini batch setting where you are?
Correct.
So that's where I have a problem, because the inverse that you compute with this on a mini batch is not an unbiased estimation of the original inverse. And so you will get, so my experience has been when you have this error in your estimate, the inverse can be arbitrarily far away and you are likely to be misled in many directions. I'm not sure if that happens in your case, but in general, that is a concern. And that's why if you're going to use full batch, you are better off using a limited memory scheme than a diagonal approximation.
I see. Point taken. I'm sure that problem exists, but so the problem here is to detect like outliers in the data, basically. So I'm not sure how that drawback will manifest here. Maybe we miss out on the recall, or maybe it introduces false positives as a side effect. Got it. Yeah. I see. No, but actually, regarding the speed for SGD, I mean, so you're saying SGD in a batch or SGD as it's mini batches?
SGD with mini batches and your natural gradient with mini batches.
Right, but so it does. Here it doesn't show that it is slow.
Oh yeah, this is what I can't say. Your problem might have some specific characteristics that does not cause such problems, but there is nothing mathematically that you can show that the direction of descent through natural gradient is going in the right direction all the time.
Got it.
That's the only thing. Because you need that unbiased, that structure for you to show convergence at some point.
So if we tried in a batch mode for natural gradient,
That would be good. If you're doing batch, you might also want to try LBFGS, which is just
because our data is so huge, I mean, batch would.
So there are alternate things that you can do, but it involves running at extremely tiny learning rates where you don't have to invert, but you can do some kind of an iteration scheme that converges to the new natural gradient direction in the limit. People have done it and shown it to work for very limited problems, but that is the other way to go for that.
I see. Can you send me some pointers?
I will, yeah.